All right, hello everybody. Today we're going to talk about Calc Lesson number 2. So we're going to pick up where we left off yesterday with talking about graphical limits, a quick review. Then we're going to talk about how you would find limits from a table. And then we're going to talk very briefly about an introduction to 1.3, which is how you would evaluate limits analytically. And analytically is another word for algebraically. So first, a quick review of what you did during the first lesson. How do you evaluate limits graphically? And that's, of course, if they exist. So just as a quick review, take a look at the graph of h of x here on the right. If I was going to ask you in A to find the limit as x goes to -1, hopefully you remember, of course, that little negative sign up there in the superscript. That means that you're approaching -1 from the left-hand side. So if -1 is here, and you're approaching it from the left-hand side, then you're going to be approaching a y value that appears to be equal to 1. In part B, you're approaching the same value, -1, but from the right-hand side. So now you're approaching from this piece here, and you're getting closer and closer to a y value of -2. Of course, remember, even though there is an open circle, a limit just means you're getting closer and closer and closer. We don't actually care if you ever get there. In example C, when they're asking you for the full limit, it means you have to compare the left side and the right side. If they are not going to the same spot, which they're clearly not, then we would say that the full limit does not exist, and that's DNE for short. Don't confuse that with an h of. So an h of -1 means at x equals -1, what is the corresponding y value? If you look at your options for corresponding y values, you're of course going to choose the closed circle, which means you would get an answer of. So the next way for which you might be asked to find a limit is by using a table. And by table, I mean either one that I've given to you or more likely one that you're going to be asked to find on the graphing calculator. So here is the function in question, x squared minus x plus 2. This is, of course, just a regular quadratic. What we're trying to do is we are trying to find the limit as x goes to 2. So again, we don't necessarily actually care exactly what happens at 2, but we care what happens as we're getting closer and closer and closer. So take a look at the two parts of the table that I've given you here. Over here on the left-hand side, notice that the values of x are getting closer and closer and closer to 2 from the smaller side. So that essentially represents the left-hand side limit. Then take a look over here at the second table. Again, you're getting closer and closer and closer to 2, but this would give you the right-hand limit, because if you're coming from the larger numbers, that's the right-hand limit. If you're coming from the smaller numbers, that's the left-hand limit. And take a look what happens. As each of the x columns get closer and closer and closer to 2, what's happening to the y columns? Well, hopefully you would agree they're getting closer and closer and closer to 4. If you take a look at the actual graph, because this is just a regular quadratic, it's well defined, and the point 2, 4 is actually a point on the graph. So again, notice that your left-hand table is your left-handed approach. The right-hand table is the right-handed approach, and it appears without question that as x goes to 2, the limit is approaching 4. For these questions, no matter how you're asked to solve them, don't forget to actually answer the question. The ultimate question is what's the limit, so always make sure that you answer it. If you're wondering, well, could you just plug 2 into the equation and get 4? The answer is sometimes, and we'll talk more about that shortly. Let's talk about a more complicated example and why you would need to use a table as opposed to not. So here, take a look at the function x squared minus 1 over x minus 1. What happens at x equals 1? Well, like I mentioned on the previous slide, can you just plug 1 in? Well, let's try it. If everywhere there's an x, I plug in a 1, I'm going to get 1 minus 1 over 1 minus 1. Unfortunately, that gives me 0 over 0. As far as 0 over 0 is concerned, that doesn't tell us anything. That is undefined. That actually has a name. It's called the indeterminate form, which means we cannot determine anything about the limit from 0 over 0. So the unfortunate thing here is I cannot actually plug in 1. When I plug in 1, I'm going to get something that's undefined, whether I do it here algebraically or whether I do it on the graphing calculator. The good news about a limit, though, is that you don't actually have to plug in 1. You just have to plug in the values that are closer and closer and closer to 1. So this is where a table really is helpful. Here I've also shown you the graph, and of course, just to remind you where the graph comes from, even though I can't plug 1 in right now, if I was to factor the top using the difference of squares and factor the bottom, those x minus 1s would cancel. that would leave me with an x plus 1, which is just a line, which is what I see here. Of course, because of the cancellation, there would be a whole. The x value of the whole would be 1. If I plug the y back into the reduced form, I get 1, 2, and that's exactly where my whole is. But again, that seems like an awful lot of work to kind of get to the fact that I can't actually plug 1 in. So here's where the graphing calculator really is helpful. I've shown you a picture over here on the left. Again, here are the values that are approaching 1. And again, 1 is the magic number. It's a different magic number in every problem, but I have to tell you what it is. So here's your left-handed approach as x is getting closer and closer to 1 from the smaller side. Here's your right-handed approach as x is getting closer and closer to 1 from the right-hand side. Hopefully, if you take a look at these values, you can see that where they're going to meet is a value of 2. So what is the limit as x goes to 1? It is actually 2. And again, don't forget to answer the question. How do you yourself make a table? Well, here's a little reminder. I'm going to pull the calculator up in a minute, but here's a reminder of how you would use the graphing calculator. You're going to type the equation into the y equals. You're going to press second window. That's going to bring up your table set. And that's where you go ahead and make all of your changes. So again, I have that little box there for you to look at. And now let's actually go and do it. So if you had a graphing calculator handy, you certainly might want to take it out and look at it. So let me go ahead and pull up my graphing calculator. So here's my y equals screen, and I typed in x squared minus 1 divided by x minus 1, and of course I use parentheses, always use parentheses. If I go ahead and press the zoom, and I press zoom standard, that gives me my 10 by 10 grid. So notice I see the line, but I don't see the whole because the whole is so small. So looking at a graph, this is where that's not a great technique and where the table really does help. So notice that if I pull up the table, I'm only seeing the integers, okay? I see the error here at 1, but the truth is 0 and 2, while those are close to 1, they're not close enough. So I need to get closer and closer. So here's the easiest way for you to do that. Press second window, and that brings up something called the table set. If you take a look here at the table set, you're now allowed to make some changes. So the table start, that says where do you want your values to start. So right now it's at -3. I could change it to 0. I could change it to whatever I want. So go ahead and change your table start to whatever you think. The change in table is how much you want it to go up by every time in the x's. Generally, it's set to 1, but you can set it to 0.5 or 0.1 or 0.01 or 0.001. Again, that's a lot of work. The best way for you to do it is to click down here where it says independent variable. That's the x. The auto means it's going to do it for you automatically. You want to go ahead and change it to ask. By changing your independent variable to ask, if you now pull the table up again, notice that it's blank, which means you can type in whatever you want. So I'm trying to find what's happening as I'm getting closer and closer and closer to 1. So maybe I want to start by plugging in 0, and I want to see what happens. Then I want to plug in 0.25, and I want to see what happens. Then I want to plug in 0.75, and eventually I want to plug in as close as I possibly can to 1, which means I'm going to plug in 0.9999, which means I'm getting so close to 2. Now, obviously, I'm not actually going to get there. It's really just because of the rounding. Let's say that I wanted to approach it from some higher value. So again, slightly bigger than 1. So let's say that I wanted to do 1.9. Let's say I wanted to do 1.5. Let's say I wanted to do 1.11. As I'm getting closer and closer and closer to the magic value of 2, or I'm sorry, the magic x value of 1, the y values are getting closer and closer to 2. So if I go back to my PowerPoint here, again, just to reiterate, even though the table didn't look exactly the same, what I do by setting it to the ask is I'm now allowed to type in, sorry, let me just get my pen back here. I'm allowed to type in these values of x from the left-hand approach, these values of x from the right-hand approach, and then I'm going to ultimately see that the y values are getting closer and closer and closer to 2, which means that's going to be my final answer. A little bit of a note here about rounding and about 0. So if you type something into the table for x, whatever it shows you for the y, however many decimal places, you can just go ahead and copy that for your answer. And lastly, if you get anything that has an answer with an E, that essentially is scientific notation, which means the number is very, 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 very small, which essentially means that it's 0. So again, to reiterate, the indeterminate form, that means that plugging the value in does not work and you cannot give me an answer. These are all the different indeterminate forms, but we're going to focus mostly on 0 over 0. So anytime you get 0 over 0 algebraically, that's bad, and it means you need to do something else. So here's an example of a problem that's already done for you. So finding the limit as x goes to 5 of x cubed minus 125 over x minus 5. If you tried to plug 5 in, you would again get 0 over 0, which is no good. Let's say you went to the graphing calculator. Let's say that you plugged in some values that were very, very close to 5 from the left-hand approach. Let's say you plugged in some values of 5 that were very, very close from the right-hand approach. Even though at 5, the function is undefined, you can clearly see that from the left side and from the right side, the numbers are getting closer and closer and closer to 75. So since they're approaching the same number from both sides, that is in fact the limit. Another example here, a more complicated problem with a radical, but again, go to the graphing calculator, type in the equation, plug some values of, in this case, t from the left-hand approach, from the right-hand approach, you're getting closer to 0.166667, and hopefully you remember that that approximately is the fraction 1 over 6. Here's a more complicated example with some complex fractions. So if you're going to type this into the graphing calculator, you just have to be really, really careful with parentheses. You would have to put parentheses not only around the x over x plus 1, you also have to put a big set around the top and a set around the 4/5 and a set around the denominator. So when in doubt, use extra parentheses. Again, here is a reminder of how you would do it on the graphing calculator. Go to the y equals, change it to ask, and it will stay ask until you change it back. So you're going to want it to be ask at least for the next couple of days. Here's my left-handed approach as I approach 4 from the smaller values. Here's my right-handed approach as I approach 4 from the larger values. Clearly, I can't actually put in 4, but it appears that as I get closer and closer, my actual limit, don't forget the answer, is approaching 0.004. Here, we've actually seen this function before. We saw it on the summer packet, the absolute value of x over x. And again, I can't plug in 0 because I would get 0 over 0. Something interesting happens here in this problem, though. As I plug in any positive value, I'm always getting back a value of positive 1. That is this horizontal piece right here. As I approach from the left-hand side with the negative values, I'm always going to get back -1, which is this piece right here. Notice that on the y-axis, they're open circles for both because I can't actually plug in 0. So here's the first time in a table that the left-handed approach is actually not equal to the right-handed approach. So here's the thing. When you have a table and they are not approaching the same value, then the answer to this problem is does not exist. The limit does not exist because the left side and the right side are approaching something different. So that's one of the times in a table where a limit does not exist. Here's a second case. So this is the limit as x goes to 0 of the sine of 1 over x. And just as a note, if you were going to use your calculator for this, you'd have to use radian mode because of the fact that you're putting in pi's. So here, as I plug in different values of x, look what's happening to the y's. First, I get a 1, then I get a -1, then I get a 1, then I get a -1. So it seems to be bouncing back and forth. That is actually called an oscillation. Oscillating means it's jumping back and forth between a couple of different numbers. So here's another example of a limit that does not exist. And the reason why is because it's not approaching anything. It's jumping back and forth between +1 and -1. So the limit cannot exist if the numbers are jumping back and forth between each other. So just to summarize those previous two examples, there are 3 cases total where a limit does not exist. So we've already seen 2 of them. Here's the first one where the 2 pieces are going to different places. And just so you know, that is called a jump. A reason why is because you essentially have to jump from one piece to the other. So if the left-hand limit and the right-hand limit don't agree, that is the first case for which the limit does not exist. This was the second one we saw, and this is when there's an oscillation or it oscillates. You might have heard that in physics. And again, that means that the y values are jumping back and forth between two different numbers, in this case, 1 and -1. That is the second case for which a limit does not exist, if it's jumping back and forth. Here's the third case for right now for which a limit does not exist. So we're finding the limit as x goes to 0 of 1 over x squared. Hopefully you remember from your rational function days, there's a vertical asymptote at x equals 0. It's getting bigger and bigger and bigger on the left side and bigger and bigger and bigger on the right side. You're trying to find the limit as x goes to 0. So look what happens if I pull up my table. As I'm getting closer and closer and closer to 0, the numbers just keep getting bigger and bigger and bigger. They're going to travel off to infinity forever and ever and ever. A new calc word that is called unbounded behavior. For now, if the values are getting larger and larger and larger, going to infinity, that means they're not actually going anywhere. So as far as we're concerned, this is the third case for which a limit does not exist. Now, be warned, that will not always be the case as we get further into the chapter, but for now, we're going to call that a does not exist. Okay, last but not least, what if using a graph or a table is just too much work or we don't have the resources? You can try to find a limit analytically, and another word for analytically is algebraically. So here's what you're going to try to do. You are going to try to plug in whatever the limit a value is using something called direct substitution. That means just try to plug it in. That will only work if the function is well behaved and continuous. If it does not work, you're going to have to do some kind of algebra first before you can plug it in. So today we're going to do just basic examples. You'll do harder ones tomorrow. But in order to do this, we're going to use all the properties on the following page. Don't really worry too much about writing them down because the truth is most of them are common sense. So here are your first set of limits. If you're trying to find the limit as x goes to something of a constant, there's nowhere to plug the value in. Your answer is just the constant. If you're trying to find the limit as x goes to some variable, plug in the number, and that's your limit. If you're trying to find the limit as x goes to some number of x to the n, plug in whatever the value is, evaluate it, and that's your limit. Basically, direct substitution means try to plug it in. When it comes to a radical, try to just plug it in as long as what you're doing is defined. So for example, you can take the square root of a positive. You can't take the square root of a negative. You can take the cube root of a positive, and you can take the cube root of a negative. So as long as the function is defined, direct substitution will work. Here are some other limits. Let's say you're being asked to find a limit, but then there's some multiplier in the front. Well, find the limit and multiply it by whatever the constant is. Let's say you're trying to find the limit of a couple things being added and subtracted. Plug it into each, find each individual limit, and add them up. If you're trying to multiply limits, find them each and multiply them. Quotient property says divide them. Power property says find the limit and then raise it to whatever the exponent is. The truth is, the bottom line, it all boils down to try to plug it in and see if you can do it. If you can, great, that's the answer. This is showing you that if you have a polynomial, you can plug the value in. And if you have a rational function, you can plug the value in some of the time. So again, it all boils down to the fact that you're going to try to just plug it in. So the limit as x goes to 5 of 2x squared minus 3x plus 4. If it says do it algebraically, you're going to try to just plug 5 in for all the x's. So everywhere there's an x, put a 5. This is kind of just showing you some fancy limit notation. You don't have to worry about that. Everywhere there's an x, put a 5. If you get an answer, congratulations, that's the limit. And in this case, it's 39. Here's another one. You're going to x equals -2. Your first step is to try to just plug -2 in. So everywhere there's an x, put a -2. See if you can do it. Look at that. You can. You get an answer. That's the limit, -1 over 11. Couple together. How about the limit as x goes to 2 of x cubed? Well, everywhere there's an x, put a 2. Cube that bad boy. The limit is 8. The limit as x goes to 4. Plug it in. The limit is 32. 3 pi over 4. Ooh, the tangent of 3 pi over 4 You'd have to think back to your unit circle. 3 pi over 4 is in the third quadrant. That's negative root 2 over 2 and negative root 2 over 2. And if you plug that in, you get a value of positive 1. Here, 4 plus 10 plus 4, the limit is 18. Here, we already know the top is 18. Plug a 2 in the bottom, you get 6. The limit is 3. So again, the moral of the story is if you can plug the x value in and it gives you an answer, congratulations, you have found the limit. Anything with trig, you can, of course, use the graphing calculator, but if you're plugging in pi's, you, of course, have to make sure that you're in radian mode. Obviously, it would be no fun if direct substitution worked all the time. So what happens if it doesn't work? Well, there is a bunch of different techniques that you're going to have to employ. I'm just going to show you the first one. So let's say you had x minus 1 over x squared minus 1. If you tried to plug in 1, you would sadly get 0 over 0. That's the indeterminate form, and that does not work. Good news, though. If you factor the bottom, you can then reduce. That reduces you to 1 over x plus 1. Now you can plug in the 1, calculate the final answer, 1/2. So that's the only strategy you're going to have to use tonight other than just plugging it in. Factor, reduce, and then plug it in. One more, trying to plug in 1 from the get is going to give you 0 over 0. Sad. Factor the bottom, reduce the common factors. Now you can plug in the 1. Then you can find a final answer. So here is calc homework number 2, and notice that it is 2 pieces. So piece number 1 in section 1.2, there are a couple problems finding limits from a graph, and then I think just 2 tables. So go back and review that graphing calculator stuff as needed. Then this is all your algebraic stuff, and 90% of the questions, you can literally just plug the x in and get the limit. So I know it kind of looks like a lot of problems, but I promise that it's not. Remember that the full answer key is posted for you to check as you work. And of course, even though we're going to go over the homework on a daily basis, it's not going to be checked until the assessment day. So, don't put it off too long and don't fall too far behind. All right. Thanks, guys, for tuning in, and we will catch you next time.